into SolidWorks. It's a separate piece of software, but you use it when you're in SolidWorks is kind of the drive home point. And this is the plastics dialog. It's integrated into SolidWorks. It's very similar to SolidWorks. And plastics, I don't know if Gary's really told you, is really broken down into 3 separate kind of sections. There's the fill, which is sort of like when you inject hot plastic into the mold. Yep. Then there's the pack, which is where the plastic goes from its liquid stage to its solid stage, and it cools down. And then there's the ejection. And SolidWorks has different, plastics has different sorts of products for those different stages. Plastics Professional is the fill stage. Plastics Premium is the packing stage. And then there's a new product, like it's brand new, and then that's for warping. That's when it gets out of the, that's when it actually becomes ejected. And you can see warpage and stuff like that. But I'm going to get started in creating a simulation here. What I'm going to do is I'm going to go through different configurations of this part, and I'm just going to hone in and then optimize until we get to our final design. And that's pretty much the way it's going to work. I'm going to change various parameters here and there. Let me know if you have questions throughout some of it. Some of it's a little bit technical, but I'll try to keep it reasonably simple. Okay. So the first step is to create what's called a mesh. And the mesh is really just a way that our simulation products break down this complicated geometry into something that's small and like easily workable. And so plastics breaks down the model into triangles, and it's easier to figure out the flow of plastic through a triangle than almost any other shape. And so that's why it breaks it down into triangles. Okay. It's a little bit technical, so I'll just kind of skip over it. The triangle size is can be manipulated here. I'm just going to enter in some values. And then I'm going to have some local refinements so that the triangles that are going to be representing this geometry can pick up on these small sort of faces and edges and things like this. And so these triangles, all of these triangles, are kind of come together to represent the geometry that is this top cover. That's really the way to look at it. Okay. So once we have the mesh in place, we actually open up the plastic software to a whole bunch of other features. And if we wanted to get really big into detail, we could certainly do that, change things like the temperature, the machine that we're going to use for this, gate locations, and things like this. But plastics comes with a set of defaults that we'll just use, and we'll just keep it really simple. So what we're going to do now is select the plastic as well as the gate location. And the gate location is where the part is going to be filled from. Okay. So what I'm going to do is I'm going to select the polymer. And as you can see, we have a huge library of plastics that that come standard. And all of these plastics have their own material properties with viscosity and specific heat and stuff like this. But if you have a couple plastics that you use more often and they're not in this database, you can actually add them manually. It's not a big problem. So I'll just go ahead and select this polycarbonate. It's like a generic sort of polycarbonate, and then click OK. And I think there are, by the way, I think there are like 4,000 plastics in that library. Okay. So the next stage is I'm going to select the gate location, and the gate location is sort of like where I'm injecting plastic into. Okay. As you can see, it's pretty, I mean, all of the whole user interface is pretty easy to kind of pick up on. It's not terribly complicated or anything like that. but as you kind of use the software more and more, it'll become very, very familiar. So I'm going to inject the plastic from location. And after that, I'm actually, all of these defaults, I could get into what sort of machine and sort of what kind of flow settings. But I actually have all of these filled in with the defaults right now. I can just run this. And this is currently running. As you can see, I don't know if this is going to update very well with time, but this plastic part will fill in. Yeah, can you see that?
It's lagging a little bit, but yeah, we can see it happening.
Okay. So this is filling in plastic with time, and one of the key advantages of this is that you can see the plastic fill up, and if there is a problem of some sort, you can actually stop the analysis in the middle. You can go back and you can make a change as necessary. And already I can see that there are a few problems. Take a look at these ribs right here where my mouse is.
Yep. What
you'll see is that we have two flow fields kind of coming together, and that's going to create something called weld line. And this phenomenon is caused by something called the racetrack effect. And that's where plastic rushes in from one side much faster than it does the other side. And as a result, we kind of get these weld lines at these locations.
Okay.
And weld lines are really not ideal because you can see weld lines in plastic parts. And like with a plastic part, you want to kind of look pretty. You don't want to see those weld lines.
Yeah.
So it's not good in that sense, but it's also not good in the sense that the plastic at that location isn't going to be as strong. So if you can possibly eliminate the weld lines from all of those critical locations where it's going to be visible and where it's going to be, where it's going to need to hold up to strength, that's ideal.
Okay.
And now that the analysis is finished, we get this little results advisor on the right-hand side. And this tells us exactly what we're looking at as far as our results. But the fill time, I'm just going to close this for the time being. The fill time is the amount of time that it takes to fill up the part. And what I can do is I can animate these results. And this just animates what we saw while it was actually solving. And we can see that it only takes about 2.7 something seconds for this to fill completely. And that's actually pretty quick. But one of the problems that we see are these weld lines that we were kind of noting earlier. So what I'll do is I'll stop this, and I'll take a closer look at the weld lines. And as you can see, we got weld lines all the way through the part over here, and we got some weld lines that are going to cause some issues over here as well. So we're going to try to do our best to eliminate that. One of the ways that we can do that is reduce the wall thickness over here. And right now we're dealing with a pretty thick wall over here. We'll just reduce that and try to see if we can force the plastic to go through these ribs first before it goes through the walls.
Okay.
So the other thing that I wanted to show are these air gaps, or air traps. And as you can imagine, if you fill a plastic part, you're pushing out air as you're bringing in plastic. And that air, that needs to escape. And it's best if that air has a pathway to escape through. For example, when you have the two mold sides, the two cavities, it's best if the air can just sneak in between there. And if it doesn't, you'll get these air traps at these sorts of locations. And what that means is that you'll get sort of a pocket here where it won't fill up completely, and you might run into issues there. It can also cause sorts of some sorts of catastrophic errors, like you can get like tiny explosions or cracks within the cavity itself. So it's not ideal to have air traps in some locations, especially where it can get trapped. The other thing that I wanted to show was something called the cooling time. Now, the cooling time is the amount of time that it takes to cool the part once it's in the mold. And as you can imagine, like I said before, we have the 3 stages. There's the filling, I guess the cooling or the packing, and then there's the ejection. And all of those 3 components kind of add up together with time to determine your total cycle time. And so if we can reduce the total cycle time, we'll end up getting a less expensive part because the total cycle time is reduced. So right now, we're looking at a cooling time of 60 seconds, or a little bit higher than that, whereas the fill time was 3 seconds or thereabouts. So this is a really, really significant time here. And what we're going to try to do is reduce this as much as possible. Hopefully get it around 30 seconds, if that's possible. So what I'll do here is I'll close out of here, and we'll take a look at a part that's a little bit thinner. And what we're hoping is by looking at this thinner part, we're going to reduce the cooling time because the thickness is directly correlated to the cooling time. But what we're also going to do is hopefully fix some of these racetrack effects issues that we're running into. So I've already run this. I'm not going to set this up again. But what we'll do is we'll just go straight to the results.
Okay.
And this is, let me know if that updates for you.
Yeah, I can see that now.
Okay. So this shows that there are parts of the plastic that haven't filled up all the way.
Yep.
And this is known as a short shot. What this really means is that all of the plastic cooled before it got a chance to reach the end of the mold. And that's going to be a problem because we're only going to be left with only a part of a part, really.
Yeah.
So that's obviously not very ideal. So we actually overshot the thickness a little bit, and we're going to have to bring that back up. But without running this sort of plastics analysis, you would never really know that that would happen. Okay, so I'm just going to go ahead and change the configuration to a thicker wall, slightly thicker. So this wall is slightly thicker than the previous one, but not as thick as the one before that. Let's take a look at the results for that and see if that filled up all the way. Okay, so right now we're looking at the fill time, and it's looking like this filled up all the way, which is good. The fill time is also reduced to 2 seconds, where before it was 2.7 seconds, which in the grand scheme of things isn't really a big deal considering our cooling time was 60 seconds before. Let's try to look and see if we can hone in on these weld lines. Okay, so we're still getting a lot of weld lines in these locations. So it doesn't look like we're going to be able to fix this with our current gate location. Right, so what we'll do is we'll focus on a different gate location and see if we can eliminate or get rid of or reduce these weld lines as much as possible. But before we do that, let's look at the cooling time. So before, our cooling time was over 60 seconds, and now we've reduced the cooling time to 27 seconds. So that's pretty much made our total cycle as far as the fill and pack reduced by half, saving us a lot of money in production.
Yep.
Okay. All right. So let's consider that other configuration with a different gate. So in this configuration, we've moved the gate to over here. And our hope is that as this fills up, it's going to go through these ribs without kind of racing around. And I think we'll be able to do that with this sort of configuration. So I'll just take a look at the results. And we can animate the results. And as you can see, any sort of racetrack effect is greatly reduced with this. There's a little bit of a racetrack effect over here, but it's not nearly as bad as it was.
Yeah.
So that's great news. The other thing that we should check out is something called the pressure at the end of the fill. And the pressure at the end of the fill is sort of like how much pressure the machine needs to subject onto the plastic in order for the plastic to fill up all the way.
Okay.
And if you can imagine it, like if you need a lot of pressure to fill up a plastic part, you'll need a much larger machine than a part that is easy to fill up with plastic. So if you can get a smaller machine, you'll potentially save a lot of money that way. And right now, we're working with a fill of 47 megapascals, which is a lot of pressure that the machine is going to need to fill. So that's sort of like a medium-sized machine. A medium to a large-sized machine would be needed in order to get this much pressure in order to fill this part. So what we'll do is we'll consider a different, we actually have a few options that we could do. We could change the gate size. We could do a number of things. But what we'll really do in this case is we'll change the plastic from a polycarbonate to an ABS polycarbonate mixture. And what that means is you'll have to take a look at the material properties to see what that really means. But in this case, the fill time is the same. It's just that the pressure at the end of the fill is greatly reduced. So that's gone down from 48 or so to 38. So that's a pretty big reduction in the amount of pressure that it takes to actually fill this part. And the properties of these two materials are pretty much the same, other than the pressure at the end of the fill. So that's great news. So this might lead us to a smaller machine that we'll be able to use. Okay, so in this simulation, we actually have the pack results as well as the flow results. So this is the plastics professional. This is the plastics premium results. You'd only get this with plastics premium. And we can look at, let's see here, the volumetric shrinkage at the end of the pack. And this is sort of like how much the plastic shrinks after it's been injected and it's cooled. You can imagine all objects, when you heat them up, they expand. When you cool them down, they shrink.
Yep.
And as this cools down, it's going to shrink a little bit. And the key is to make the shrinkage as small and as uniform as possible. If the shrinkage isn't very uniform, you'll get something called warpage, where one part will shrink more than the rest of the model, and the end result will look quite a bit different than you were originally intended. So this shows a shrinkage of 3% at its maximum, and you'll get shrinkage here. And what that really means is you'll probably just get a little bit of a dip at this location, but it's only 3% shrinkage, so it's really not that much anyways. So you probably wouldn't see something like that. So that's just a little peace of mind that the actual product that you set out to design is going to be the product that you'll get in the end.
Okay.
So the next thing I wanted to show was, now that we've designed our part, sometimes it's advantageous to actually show how you would fill a family like mold. And the reason why you would do something like this, fill all of these components at the same time, is to make sure that all of the parts look or appear the same way. And what can happen is, if you don't do it this way, if you were to fill this on a different day than this component, what would happen is the plastic would sort of look dissimilar, and they wouldn't necessarily warp the same way, and so they wouldn't necessarily fit together as well or look as good together. So one of the challenges of designing something like this is to actually get all of the cavities to fill at the same time. So I'll take a look at the fill time for this, and what we'll notice is that certain cavities fill faster than other cavities. I'll just go to the top here and animate this. So what we'll notice is that these top cavities of the smoke alarm fill much faster than the bottom cavities. And what that means is that these, especially towards the end, they might not look exactly the same because the plastic would cool at different rates.
Yep.
So what we want to do is change these gates, or these runners, pardon me, so that the runners make these cavities fill at the same time. As it turns out, we have a runner balancing, I guess, like little application that sits on top of here. And what that'll do is that'll change the size of the runners automatically in order for these cavities to all fill at the same time.
Okay.
And there would be no other way to do this. If you didn't have plastics or a program that could do this, there would literally be no other way to do this other than guesswork. So what I'll do is I'll animate this. And we'll see that everything fills at the same time.